You know what's great is that once we start practicing or using something, we become more familiar with it and we become better at using it and working with it. The same is true for the IPv4 routing table on a Cisco router. Well, we've come to that part in our journey in this skill regarding interpreting a routing table where Bob has called us once again and has asked us to come into their site and take a look at their network and help explain to the manager why a packet is taking a certain path through the network. Now, to do that, we're going to have to look at a few routing tables, but together we can knock this one out of the park. Let's take a look at the topology. So here's our enterprise topology, and we've got a user over here sitting on VLAN 10. Now, when we say we have a user sitting on VLAN 10, of course, what we mean to say is that we've got a computer connected to a switch port, and that switch port is assigned to VLAN 10. And then on top of VLAN 10, we have a specific IP network address space that we're using. So in this topology, VLAN 10 is using the IP address space here in Arizona of 10.16.0.0 with a 24-bit mask. That is VLAN 10. This host is at .10, and the default gateway that this computer is using is 10.16.0.1. And that IP address of 10.16.0.1 is being supported by Core 1. It has a switched virtual interface with that exact IP address of 10.16.0.1. And that interface, because it's in VLAN 10, is the interface VLAN 10, that layer 3 interface on Core 1. So let's focus our attention over here to Nevada for a moment. Over here in Nevada, we have a network address space of 10.16.8.0. In fact, that is being used for VLAN 1 out here. And there's a host on that VLAN of .111. And now for the questions they want us to answer. And that is, if the client on VLAN 10 does a ping to the IP address in Nevada, can we explain the path that's going to be taken and why that path is being used? And the answer is yes, we can. We can explain that as we look at the routing tables on Core 1, on Router 1, and Router 2. And to confirm where those devices are, here we have Router 1 AZ, and up in Nevada we have Router 2-NV. And this Metro Ethernet is just representing like one layer 2 network. Just think of it like a big layer 2 VLAN that's connecting Arizona and Nevada together. And the address space that we're using on top of this network between Arizona and Nevada is 10.16.7.0 with a 28-bit mask. Now, the tricky part can be, because we have several routers involved, is like, where do we start? Where do we go look first? And one strategy would be to say, well, if we're taking a look from the client's perspective, they're going to forward that packet to their default gateway. Start there. So in our case, that would be Core 1. And then we just ask Core 1 with the show IP route, what would you do with this packet if you received it? And then go to the next hop and the next hop. So we'll do that together. And I think it'd be helpful and useful for us as we figure out this path for this packet is to jot down in a table what that next hop would be, and also what the layer 3 address of that next hop would be. And let's also throw in what the layer 2 information would look like for that next hop. So here's what I propose we do. For the destination IP address of 10.16.8.111, which is an IP address out there in Nevada, let's complete a table that's going to show each of the hops. So whatever our routing device is, let's identify what the outbound interface it's going to use as it forwards the packet. Let's also include the next router name and IP, and let's also include the layer 2 information. And so in the hands-on lab, let's do this. Let's go to this PC, which is our client PC in the virtual lab, verify its IP address. Let's verify that it can ping to 10.16.8.111. We'll also verify its default gateway as Core 1, and then we can start at Core 1 and take a look at the details from the routing table on its decisions on how to forward packets to this 10.16.8 network, and then go to each of the routers in that path and take a look at their routing tables as well. So in the lab, we're going to go to the client PC. Let's go ahead and open up a command prompt. And from a command prompt, let's do an ipconfig and verify our IP address 10.16.0.10 and also our default gateway of 10.16.0.1. And let's do a ping all the way to the Nevada device at 10.16.8.111. We'll press enter, and that works. That's great. And we can also do a trace here, TRACERT, on a Windows device, -D for don't bother DNS resolution, and the IP address of 10.16.8.111. And that's going to show us the full path right here. So the first hop is 10.16.0.1, which is Core 1. The second hop is 10.16.6.5, which is R1. And then 10.16.7.6 is going to be R2. That's the Nevada router. And then the final destination is 10.16.8.111. So let's make a road trip to Core 1, and we'll just ask Core 1 in the routing table about its forwarding decision to get to that 10.16.8 address. So we'll go back to our administration machine, which is DCNUG. We'll open up MT-PuTTY, and we'll open up a console over to Core 1. So here on Core 1, if we do a show IP route. Now, if we do a show IP route, there's lots of output it's going to generate. If we want to thin that out a little bit, and we know we're looking for the 10 networks, we can do a show IP route space 10, the classful 10, 000, press enter, and that will just show us the 10 networks. And if we want to thin that out a little more, we could do the same command, show IP route for the 10 networks, space, a pipe symbol, space, the keyword exclude, and then you could include something from the lines you don't want to see. So if we want to exclude any output that has the letter L in it for local routes, we could type in exclude space L, press enter, and that would exclude those local routes. So if we look at the routing table for the 10.16.8 network, it's right here. So this was an OSPF learned route, hence the routing code over here. The network is a 24-bit network of 10.16.8. There's an administrative distance of 110 because that's the default for OSPF. The cost of that route is 3. And the next hop is 10.16.6.5. And the exit interface that this router, Core 1, is going to use to forward to that next hop is VLAN 40. So let's pause here with this route in mind, and let's add that information to our table. So for Core 1, the outbound interface is interface VLAN 40. Now that's based on our routing table. We're just taking its word for it. So if we go back and take a look, right here, the egress interface is going to be VLAN 40. And the next hop is going to be 10.16.6.5. So let's add that to our table. So the next router is 10.16.6.5. And that IP address in our topology is owned by Mr. R1, R1AZ. That's our Arizona router. Now the next question is, if Core 1 is going to use its outbound interface of interface VLAN 40 and send it to the next hop of 10.16.6.5, my question for you is, if we looked at the layer 2 information as Core 1 is forwarding this packet over to router 1, what would be in the layer 2 destination address? Because I know the destination IP address is going to be the same all the way across, but every time we go across the routed interface, we're going to be re-encapsulating using a new layer 2 address. And if you're thinking, well, Keith, the layer 2 information, if this frame of data is being forwarded at layer 2 over to R1, that frame of data at layer 2 is going to need to have layer 2 information so the network can forward it to the right device. So if we go back to Core 1 and we asked it, hey, what is the layer 2 address for 10.16.6.5? If Core 1 has forwarded a single packet to this IP address, it's already done the ARP, and it should be in the ARP cache, the layer 2 information. So here on Core 1, we can do a show ARP, and check this out. We're looking for the next hop, 10.16.6.5, and there it is. So there's our entry, the layer 2 information for 10.16.6.5. And so at layer 2, Core 1 would be using this layer 2 information as it re-encapsulates that packet in corresponding frame to forward it on to router 1. So back at our table, we can just go ahead and say this is going to be R1's MAC address. So that frame of data is sent, router 1 receives it, and then it looks at the layer 3 information, the destination IP address, says, oh, 10.16.8.111, what do I do with this? Well, let's go ask him. Let's go to the console for router 1, and we'll ask that question via the command show IP route. So back at our admin PC, we'll open up a tab for R1. So we'll go ahead and click on R1AZ. And then from here, we'll do a show IP route. So you can do the whole thing. It's sorted, or you can search for just the 10, or you can search for just that specific network. So if we look for the 10.16.8, here it is right here. So it was learned via OSPF. As a result, it has an administrative distance of 110. The cost is a 2. Here is the 24-bit network. The exit interface is going to be gig2/0, and the next hop in the path is 10.16.7.6, which happens to be an IP address associated with R2. So let's add that information to the table. So now this is R1. The outbound interface it's going to use is gig2/0. The next hop is going to be 10.16. And I need to go back look again. Let's take a look. 10.16.7.6 is the next hop. Great. And that is owned by router 2, which is the Nevada router. And then because the connectivity between R1 and this next hop R2 is Ethernet, what would be if we looked at the layer 2 information as that packet is being sent from R1 to R2, whose MAC address would be set up as the destination MAC address in that frame that's being sent over to R2? And if you're thinking, well, Keith, if it's going to R2, the frame is going to have R2's layer 2 address. And you'd be right. It'd be R2's MAC address. And if we wanted to see what that is, let's go ask R1 if he knows what R2's MAC address is. And there's a good chance that he does, because he's using them as an next hop for some packets. So we do a show ARP and press enter. And we look for the ARP entry for 10.16.7.6. It's right here. So it'd be this layer 2 address that R1 would use as a destination layer 2 address when he's wrapping up that frame and shipping it off to R2. So the next question is, what is R2 going to do with it? So let's add that right here. So R2 gets this frame, de-encapsulates it, looks at the destination IP address and says, okay, now what do I do? What's my outbound interface? Is there a next hop? And what is the layer 2 information I'm going to include before I send that packet on its way? So what we need to do is let's go take a look at R2 and we'll ask the question with the simple command show IP route. So we'll open up a tab over to router 2, which is the Nevada router. And then here on router 2, we'll do a show IP route, press enter. And what we're looking for is something that will match, a route that will match the 10.16.8 network. And here is a match right here. So the C says this is a directly connected network. It's the 10.16.8 network. And the egress interface is gigabit 1/0. So let's go back to the table and confirm what this router is going to do now that it has a packet that needs to be delivered to a device on a directly connected network. So on R2, its egress or outbound interface is gig 1/0 based on the directly connected network in the routing table. The next hop is not going to another router. In this case, because R2 is directly connected, it's going to this bad boy right here. It's going to 10.16.8.111. And router 2 is all excited, like, woo, I'm directly connected, which means as it forwards the packet at layer 2, whose layer 2 information is R2 going to include as the destination layer 2 address? And if you're thinking, well, Keith, because he's delivering it to this IP address, it'd be the layer 2 address that corresponds to this IP address. And if R2 doesn't know what that is, he would use ARP and ask and find out. So let's go back to R2 and see whether or not he already knows the layer 2 address for that destination IP address. So here on R2, if we do a show ARP and press enter, and sure enough, it has learned the layer 2 address of the host at 10.16.8.111. It's this bad boy right here. And then it would be up to router 2 to add that correct destination layer 2 address and then forward that into the network. And the switches would deliver that to the right port. And then the host at .111 would receive the frame, realize, hey, that's my MAC address, de-encapsulate, look at the IP address, say, hey, that's my IP address, de-encapsulate, and then whatever's inside, whatever goodness, maybe it's an ICMP request, maybe it's a web service request or something else, that host can now take a look at the application layer information and then make an appropriate response if one is required. So here's what I'd like you to do. If you've gone through this exercise with me and done the hands-on, whether in our lab environment or in Viral or GNS3 or a simulator or LiveGear, if you've done this summary practical application of the skills we're learning in this set of videos, I'd like you to give yourself another 10 points. So our goal is to get to 100 points. Now, not just for bragging rights, but also as we continue on and we're applying our skills and reinforcing those skills, we become more valuable. We become better at technicians and engineers in both understanding, implementing, and troubleshooting IP networks, which is the goal. We want to get really, really good at this. And the more practice that we put into it will increase and build those skills. So thanks for joining me in this set of videos. I'll see you in the next one. Meanwhile, I hope this has been informative for you, and I'd like to thank you for viewing.